Okay, let's look at quiz number 8. Quiz 8. Here we have ethylene gas, and it's being heated from 30 degrees to, let's see, 100 degrees C at constant pressure. And we want to know the minimum amount of work to accomplish that heating. Now obviously we could put it through a space heater and put work in, and that would heat it from 30 degrees to 100 degrees, but that would be a real waste of energy. If we use some kind of heat pump that we draw heat from the surroundings, let's put QS here, we can add that heat to it and accomplish the heating. Thermodynamics sets bounds on what's possible. It doesn't tell us how to do it necessarily, but it tells us what can be done. And what I want to do is just find the minimum amount of work that we'll have to do in any process that we could imagine to accomplish that heating. So ethylene comes in at 30 degrees, comes out at 100 degrees. And that's the surroundings is also at 30 degrees C. Let's convert that over to Kelvin. That's approximately 303 Kelvin. And this will be 373 Kelvin. Now you're given some information about ethylene. Let's see, the information was that it has a molecular weight of 28, a CP of 1.548. So CV is equal to 1.548. That's kilojoules per kilogram K minus R over molecular weight. If you recall, that's a relationship between CV and CP. CP minus R over molecular weight gives you CV, and that comes out to 1.548 minus 8.314 divided by 28 comes out to 1.251 BTUs per pound degree rank. I'm sorry, that's kilojoules per kilogram Kelvin. And we can then calculate K, which we'll use for later problems. K is equal to CP over CV, and that comes out to 1.237. So we have 3 kilograms per second going in at 303 K, and then it's heated up 3 kilograms per second going out at 373 K. So the energy balance is N W plus Q, W dot plus Q dot plus M dot H1 equals M dot H2, neglecting any kinetic energy, potential energy that might be associated with the gas. Or substituting for H2 minus H1, let's see, actually it's just solve for W dot, that's what we're trying to find, is equal to M dot times H2 minus H1 minus Q dot equals M dot CP times T2 minus T1 minus Q dot. And this comes, let's see, we have T2 we know. I'm going to put a little check on T2. T1 we know. Put a check on that. We know the mass flow. We know CP, so we can calculate all that. And our unknowns here are Q and W. We're trying to find Q and W are our unknowns. A little question mark there. We can also do an entropy balance, and I'll draw that with an SB for entropy balance. And that that goes something like, see, work has no entropy, so 0. N plus generated, and we're looking for the minimum work. Since we're looking for the minimum work, we'll assume the process is reversible. That's the best we can do, so no entropy generated. Let's see, plus m dot, plus m dot S1 plus q dot over t of the surroundings equals m dot S2. And from that I can solve for q dot, let's see, 0 plus m dot S1. See, q dot is equal to t of the surroundings times S2 minus S1. And we'll substitute in what we know for entropy of an ideal gas. That would be m dot Cp ln of T2 over T1. Let's put that in brackets. Minus R over molecular weight ln P2 over P1. Now, of course, this P2 over P1 will be 1, assuming the same pressure in and out. So the log of 1 is 0, so this whole term drops out. And we finally have the q dot is equal to t to the surroundings, which is 303 ln, 303 times Cp, which is, scratch that out, 1.548 ln of 373 over 303 equals 292.5 kilowatts. If you put the units in, you should come out with kilowatts. Scroll down a little bit, and now we can put that back into our energy balance, and the work minimum is equal to, let's see, that was m dot 3. Oops, I was missing my 3 up here. There's a 3 in here. Mass flow up above. 3 still comes out to the same result. Calculated that earlier. 3 times, let's see, the work is 3 times Cp, which is 1.548, times T2 minus T1, 373 minus 303, which, by the way, that's delta H times the mass flow is 325, 08 minus our heat, which was 292.5, and comes out with the minimum work that we had to do was 32.6 kilowatts. Now that's fantastic, because had we done this with a space heater and just heated that gas up by plugging it into the wall and heating it up, we've had to raise the enthalpy. That would have been 32.5 kilowatts. Here we got 292, let's draw that in green because that's a good thing, free from the surroundings, 292.5 kilowatts. I say free, really we had to have quite a machine. To make the machine that can do this reversibly is quite a lot of effort, or quite a lot of expense to have such a machine. But nevertheless, the bottom line is we can much more efficiently heat that gas with only 32.6 kilowatts. So that was question 1 of quiz number 8. Question 2 of your quiz was, suppose I start with piston cylinder arrangement and compress a gas, the ethylene gas again, from 303 K and some undetermined pressure to 1/5 of its original volume. Now we know then, we're going to assume ideal gas behavior again. We know if we compress it, we're putting work in, so the temperature will go up because we added work. as long as we insulate it and make sure that we don't have any heat. So I'll put a little insulation around this, indicate that this is an insulated system so no heat can get out. Assume all the work goes in a gas and neglect any change in temperature of the wall. So let's see, this is the entropy balance on this is, of course, when we're looking for the minimum work that we're going to do. Let's try W min. We want that to be a reversible process, and it's well insulated. Q will be 0. Call that adiabatic. And reversible, so S generated equals 0. Then we have in plus generated equals out plus accumulated. So the work carries no entropy, so that's 0. No entropy generated, nothing going out, and accumulated is the mass times S2 minus S1, which leads to S2 equals S1. If S2 equals S1, then T2, we've developed this earlier for isentropic processes. For ideal gases, T2 equals T1 times V1 over V2, which, by the way, we call that the compression ratio, to the K minus 1. And we solved for K earlier, so this is 303 times 5 over 1 to the 0.237. That's K minus 1. And that comes out to 444 K. Actually, we didn't ask for the work here, just we're asked to find the final temperature. And the choices were in degrees C, so let's subtract 273. And that comes out to a final temperature of 171 degrees C. Because we did this reversibly, we put in the minimum work. That's the minimum the temperature will rise in this adiabatic process. Had there been friction, we would have had to put in more work. That work would have gone into the gas and we would have had a higher temperature. And the last problem on your quiz had to do with an adiabatic turbine, well-insulated turbine. Okay, let's insulate that turbine, putting work in, and we're trying to find the minimum work because you asked that the work is at least how much work we're coming in at 303 Kelvin, coming out at some unknown temperature, but P2 is unknown. P2 equals 5P1. So if we raise the pressure by a factor of 5, and we have in plus generate equals out plus, well, let's assume it's steady state, so nothing's accumulated. In plus generated for entropy balance equals out, or m dot S1 plus 0, for the best we can do, equals m dot S2, or S1 equals S2. If we treat that as an ideal gas and assuming constant Cp and constant entropy, then T2 is equal to T1 times P2 over P1 to this time to the K minus 1 over K. I've done this earlier a different way. That would be also T1 times P2 over P1 to the RU over molecular weight divided by Cp. And that comes out to the same thing, which winds up being 303 times 5 to the 0.237. I'll use the K minus 1 over K method, 1.237. And that comes out to a final temperature of 412 about 412.4 Kelvin. And then we can solve for the work. The energy balance gives us the work, W dot min plus m dot h1 equals m dot h2, n equals out, or W dot equals m dot h2 minus h1 equals m dot cp t2 minus t1. And that's easy to solve for. Scrolling down just a tad, we have m dot work min. Again, this is minimum work, is equal to 3 kilograms per second. I can put the units in here so you can see them. Per second times CP, 1.548 kilojoules per kilogram K times 412.4 minus 303 K. And see, I can cancel my units. The kelvins cancel, kilograms cancel. I wind up with kilojoules per second, which we know is a kilowatt. And this whole thing comes out to work min is 508 kilowatts. If I had to do this with a irreversible turbine, and suppose it was still insulated, still adiabatic, then I would have had to do more work, and the temperature would have come out a bit higher. So there's a couple quick problems on reversible processes, and be able to do those kinds of things.